and I think we were using 2020's subset of the data, right? So let me run it for you once again. So overall, the annualized return that we were getting on the AIP stock was negative. So this stock was not a suitable stock for us. So what we were suggesting is like, in order to we took a Facebook, and let's see what is the we can use any security for and use the same code for getting the returns, expected annualized return. So if you see, Facebook gives us a 48% annualized return, which is pretty good based on this model. Let's see Amazon ticker. If I use, how much we will get 45%. So Amazon is also good. So this method basically allows us to select individual stocks or individual securities uh, based on their annualized return, expected annualized return, and we can also see the Sharpe ratio. And so we will be able to select, identify which are the, so if we have like a shortlisted 50 or 60 odd different portfolios or securities in our mind, we can run this method and check which of the securities is going to give us the maximum returns. And out of those 50, 60, we can, the top 5 and 6 we can select. So this was one of the methods that is primarily used in trading strategies. So if you will remember, Bollinger Band is also, we can track the Bollinger Bands also and all technical indicators in order to assess the trend of the different stocks. And there are other indicators also, like your RSI, which you identified, the ROC, which you also said. So these are some of the other indicators that you might use in order to judge the performance of a stock that might happen in the future, or the performance of a security in the near future, or in the coming future. Now, but there is one very important gap in this method that we had, we were doing. The most important gap in this method uh, that we had done was we have ignored one of the very important components in time series, which is called as the trend and the seasonal components. In order to predict the future or to model a time series, we have to make the time series stationary, as you would know. But in this case, simple moving average or exponential moving average, the chances of making it stationary is very limited. We generally do not uh, remove the non-stationary components from the time series, and hence our model may fail to give the accuracy or the expected result that we might expect. It might fail also, given uh, the trend and the seasonal components come into picture. Now, definitely, to a certain extent, using the other technical indicators, uh, we can keep a tap on that. But yes, uh, we need to look at an advanced model for um, identifying the performance of a particular security. So today we will start with one other different model, which is one of the most used model, which is called as the RIMA model. Um, in Nowadays, there are even more advanced model than a RIMA that has come into the market. like the wavelet methodology and the Fourier transforms. But ARIMA was primarily one of the most used methods in time series analysis. Now let's look at how we can implement ARIMA for a company like Amazon, right? So the case study that we will discuss now is it was a real-time case study that was done for Amazon in the year 2015 by a set of scientists at that time. Uh, I will not be discussing in detail about the all the different combinations that was being used, but I would briefly cover the methodology that they had adopted in predicting the Amazon stock prices or Amazon price way back in 2015, what it was going to be in 2000 and in the coming years. So with that thought in mind, let's start our methodology. So the first thing that we, as usual, we do is we import our libraries. So the libraries that we will be using in this case are the standard libraries that we have. The quant mode. The quant mode is one of the most important libraries that we have. Then we have the library. Then we will be using many time series models, which is called as like one is the most important is the forecast. Okay. Then the other library that we will use is time series. Just time series. The other library that we will be using is T series. Now T series and time series both have a few different methods that are available separately. Not getting into the details of that, but just to make it clear, uh, this will help us in converting data into a time series object. Similarly, XTS is another very important library in time series, which is used for XTS is basically stands for the extensible time series modeling. So let's start our model. The first thing that we need to do is we need to get the price of the Amazon stock, and we will adopt our very old method called as get symbols. Actually not get symbols, but get symbols.yahoo. That is what we had, and the stock name that we want is Amazon, and the date from here we will be using a from date from, let's say we are using since the model was created way back in 2015, I will take the data all the way back from 2014 onwards, right? And auto dot sign equals to F or false. So this is for getting the Amazon stock prices all the way, Amazon closing price, opening price, all the way from 2014. Um, Now we want the closing only. We want the only the price for us is only the closing price for us. So let's use the closing price. What I mean is, if you would have remembered, let me run and show it to you. So when you go in Amazon, you see the different all the values for the opening price, the high price, the low price, the closing price, the volumes, and the adjusted price. We will be using this Amazon close price, which is the fourth column, in order to get the price of the data. So basically, the returns will be calculated based on the closing prices. Let's. I will use a command called as na.omit in case there is any null values in that we want to get rid of it. And I will use again this entire thing. Actually, I can use this entire to get the fourth column, basically, right? So the fourth column data I will be having. So when I run it, uh, you will be able to see the fourth column data, which is the closing price of the Amazon stock. We know how that is how we get a fourth column in Amazon. Now let's chart our series uh, and see how the prices of Amazon have looked like. I'm using all the prices for Amazon, like the opening, the closing, in order to chart it, just for the purpose of charting it. So basically, we expect a candlestick chart, right? Let's see what it creates actually. Okay, I think it's name. I have to give the column name actually. That's what we have put into it. All right. So basically, it created a line chart, and we can see the volumes being traded and how the components have behaved over a period of time, right? So what do you see in this? What is the basic story behind it? So if you um, from the observation from this graph, upon briefly looking at the data, so you can see that the stock value increased over time since 2015, right? So there is a definite trend, an upward trend in the data all the way from 2015. Another important fact is in 2018, there was a spike, right? There was a spike. Uh, there is no apparent pattern that can be used to scale the value of the stock price because the stock price are not, the trends are not linear. And so it is very difficult to have a mathematical formula to describe the change in the curve or the fluctuations between the increasing or the decreasing prices, as you would see. But we definitely know there is a specific trend in our data, and we also know, and we can also see that there are fluctuations in our, so there is also a seasonal component in our data. So so it is the, now let's see whether there are seasonal components or not. So as you would know, or in case you um, in order to see the time series, the different components of a time series, we use a method called as decompose. Now let's decompose our this time series and look at the different components that might be present in the time series. The components are your trend component, your seasonal component, and your error component, which is your residuals, right? So we know that these are the three components in our time series. We need to isolate, or in order to make our time series, we need to remove the trend and the seasonal component or make it as less as possible, right? So let's look at how we can do that in R, basically. So before that, what I want to do is I want to take that data from 2015. Let's uh, take the data from 2015. So in order to time series data. So what I want to use is I want to convert. Now, if you will see the dates and the prices of the Amazon product, that is not necessarily a time series. We need to actually explicitly convert prices on a time series in order to apply the time series concepts, right? So what I meant is, if you would see this Amazon values, even though the first column is a date, it is not a time series as such. It is R does not recognize it as a time series. For R to recognize as a time series, we will have to use this TS function in the library called as time series library in R to make R identify that it is actually a time series object. So let's see, I want to use from um, all the way from 2015, though we have the data from, and the frequency that I want to use is like 120, right? That is the frequency I want to use. The next thing that I want to do is I want to decompose this time series. I have to, in order to see the various components of the time series, I have to use a function called as decompose. So this is a function which we will call, and we will call our time series object. And let's plot our decomposed time series, right? So this creates our time series object. Now let's decompose it. And in order to see the decomposed component, let's plot it. Now let's look at it. So you see, the first is your observed graph. The second is your trend component, so that there is a definite trend in the graph, right? Seasonal component, there is a definite seasonal component. So what you can basically see is there is a fluctuation in the stock price based on the calendar or a fiscal year. You would, if you would carefully see, the stock price, the peaks of the stock price occurs mostly around quarter 4, like July, August, and September. And there is a trough which happens around January, March. So you can see this if you would very carefully see these um, individual curves. Other than that, there is also a random or a residual error, which basically this section describes the trends that cannot be explained by the other two components, which is our trend or seasonal components. So statistically, these errors are the difference between the observed price and the estimated price. And but one thing is pretty clear from this, from what we have, is that there is definitely at times both trend and the seasonal component in our data, and we need to remove them in order to. So if we directly use a moving average method, what will happen is that it will be biased. Simply, our method of moving average will be biased based on the trend and the seasonal component. Not that the moving average method will necessarily give us a wrong value, but it will get a biased. It may give us a biased value. So it's better to remove the trend and the seasonal components from our model before going ahead with modeling the data. So let's see how we can remove our these. There is a very simple methods that we will use. Uh, what we will be basically doing is we will be taking the log of the price and we will be taking the square root of the price. And let's see how we can do that. So we will be basically using this power method is basically used for the graphs, like because we will be have once we have the logarithmic graph, it will be taking a lot of pixels in the screen. This is a standard R function that is used to limit the number of pixels that are created for a logarithmic graph. So whenever you are creating a logarithmic graph or something like that, it's better to use this PAR methodology. That yes, it is a standard methodology in R which limits the pixel sizes, right? So let's create our log price. So log price, nothing but the log of our prices. Uh, so we had the closing price data, and the log of the closing price data is what is our log price. Then what we will have is the square root of the price. What is the square root of the price is basically we will create the SQRT of the, we will use the square root of the price. The next thing that we will be, so let's plot our log price and let's plot our square root price and see how the data looks like. Right. So that first let's create this, run this, and got created. Let's plot. And now you see this. So the log prices now it is moving more or less towards a normal value, right? So what it is basically trying to do, there are many reasons why we use the logarithmic returns, but in short, the fluctuations in the price are transformed into returns that can be better compared over time and used to describe the trends. The result is a smooth curve and with a reduced variation in the time series, basically. So a forecasting model can fit more accurately. That is our more important aspect. The square root values instead of raw prices are used to scale the volatility. Now, what do we mean by volatility? Volatility basically is the spike, is the difference. And so in order to manage the volatility between points, to manage the time horizon of the stock, square root values also has a um, very significant uh, role in that. So in short, uh, basically in order to we have to smoothen our data or to remove the fluctuations in our data altogether with respect to the trend and the seasonal components. Now what we will be doing is the log prices that we have created, we will be calculating the different logarithmic price returns based on our log prices. Now let us see how we can use the create the differential price returns based on our log prices. So basically we want to use our log price as the component for creating our returns. Even your we can plot, and as we can see our square root returns are also uh, better actually. So that is how your square root price and log price are created, but it is basically more prominently we will be using the log price. So let's create our returns. So what we want to do is basically, as we know, difference of our log prices. If you would have remembered our SMA model, we also used the diff of our log prices method. So in a way, we were also trying to smoothen our simple moving average method before applying our smoothen moving average method to our um, simple moving average method to our previous trending strategy. In this case, we will be using the enhanced ARIMA model, but we will be again, I wanted to give you the difference actually between why we actually use the log prices and show you how a log price actually smoothens out our graph. And we saw that, right? It smoothens out our uh, graph much better than the original, the raw prices. So let's plot our D log price. This is not omot, this is omit. So I created, now let's plot our D log price. So if you see now values are more or less around zero. The returns, it is basically not more than, I think, 0.1 is the max, plus minus zero point 0.1. That too very few are plus minus zero point 0.1. Other than that, more majority of our returns are basically around the value of zero. So we know that we have been able to make our graph smoothened quite significantly. Let's do the same thing for our square root prices. So the square root price is basically, I will use the same thing. Instead of log, I will use SQ RT. So the square root of the place, instead of uh, let's look at uh, b square root. Okay. So let's create this and let's run it. So square root prices are more diverged compared to our log prices, but still even the square root prices have smoothened out our graph to a certain extent. Anyways, the next thing that we want to do is we want to do the ADF test on our price and D-log price. So the advanced Dickey-Fuller test is used for checking the stationarity of a time series model, right? You would have known. So in order to know whether a time series is basically stationary or not, we use the method called as the ADF test, which is also the advanced Dickey-Fuller test, which we call. So let's see the result of the ADF test. And how do we do the ADF test in R? Is simply just write ADF.test, which is part of our quant mode package or time series package. So let's the first thing that we want to do is we want to use the log price. I will do it 4 times and use the square root price, and then I will use the Dickey-Fuller test for the D-log price that we created and the D square root price. So let's look at what is the Dickey-Fuller test result for p-value for our log price. So if you see the p-value is 0.1616, it is not significant, right? Generally a p-value of 0.05 is what is a will tell us that our less than or equal to 0.05 will tell us our model is to a certain extent stationary. Even the SQRT price doesn't help us much. Now let us look at the D-log price. So if you see the D-log price, the radicular test result says that the p-value is 0.01. So our returns using the differential log prices, we have been able to achieve the model stationarity to a lot of to a lot of extent. Even using the differential square root prices passes the Dickey-Fuller test. To a certain extent, now we are sure that we we can go ahead and create our ARIMA model using the differential log prices. Now, what is the next step of an ARIMA model is to determine the the PQ component, which is the autoregressive component, the Q component, which is the moving average component, and the D component, which is the differential component. How do we determine them? We use a method called as ACF and PACF, if you would remember. So let's look at how we can determine the ACF and the PACF. This PAR method is generally I use for limiting the pixel size, as I mentioned to you. So that is fine. That's the only method that we will be using. So we will be using the D-log price mostly in our data. So let's look at the ACF values and the PACF values for our D-log price. We will also look at the ACF and the PACF values for the differential square root price, but uh, let's look at the ACF values. All right. So if you will see, this blue lines represents the line of confidence, and it spikes around the 1 and 2, the second level. So p-value we can approximately say is 2, right? Um, that's what is approximately that you may say. Now look at the PACF component. Let's zoom it. Okay. The PACF component is also almost saying it is around 2, is where the um, graph is cutting the blue line, right? So upon viewing the ACF plot for the logarithmic returns, the cutoff for a strong correlations where values basically where values no longer cross the blue dotted line, approximately is at lag 2. So, and similarly for PACF is also is approximately 2. So we can say that um, we can fairly use an ARIMA model which is like ARIMA 202. Now, why the differential component we are using 0 is the basically the D notation is approximately 0. Yeah. So let's plot our um, the differential returns now. So let's create our ARIMA model using ARIMA 202, which is P equals to 2, D equals to 0, and Q equals to 2. That is our model that we will be fitting to our ARIMA model. So for this, let's first do the returns. the next thing that we want to do is we want to create our ARIMA model, right? So let's create our time series objects first. For creating the ARIMA model, the first thing that we will be doing is we will be creating a real return variable where we will start, where we will basically store the dates. Now they as an extended time series. Uh, it will just have blank dates, like initially null dates, which will get filled up with our as and when the model runs. We will see how the model is created. Basically in ARIMA, how the model is getting created, we will be seeing that. So 2018, let's say I want to use uh, a value. I'm just storing an uh, you can say constant value which will get replaced. This is any value that I'm using which will get replaced as and when the model runs. We will see that. Percentage, the format, this is the method to format our data. So this is the common formatting method that we use in R to format our data. So if mostly you would have seen your data looks like this. So it is YYYY dash DD sorry dash MM dash DD. That is the normal format in which your time data is available, but the data that you want is basically, so that is what you are specifying. Your date is in percentage Y, means Y any number of times, M percentage, and then you have D. So this is what is the format in which the data is being streamed, will be streamed to you. Real return right now is a null date object which says that, okay, I am expecting that when the model will run, the dates will come in the format of percentage Y, percentage M, percentage T. So this will take, so the order will be YY MMDD. Basically, it is not YY, it is YY, right? Now, similarly, we also have to create our forecasted return from our uh, so we will be basically getting, based on each date we will get the forecasted returns. So make it a data frame object. A data frame, as I explained, is is like a 2 by 2 matrix which can store data, any type of data, whether it is numeric or string. We will be using a method called as forecasted, and we will be calling it as numeric. So this also I am basically uh, initializing my date and my forecast values. So this will have null. See, if you click on this, this has null. It doesn't have any no data. It will get filled up. So when we will run our models now, where we will initialize our model. So for that, what we will do is we have our DLOG price data all the way from 2015. We saw we have from 2015 to 2021. I want to create a training and a test set. First of all, that we have to do that. So in order to create a training and a test set, we have to use something called as a breakpoint. A breakpoint is the place where it will divide that till this point I have my test set result data. Now there is an important reason why we use a test set and a training set in data analytics. It is basically a more of a data analytics or a machine learning concept, if you would have, if you would see in the future, um, where we divide our entire data into training and test set. So let's see how we divide it in R. So we use a function called as floor, and we specify the number of rows. Now the number of rows of what? Of our differential log price component, right? And I want a value like 2.9 divided by 3. So that is approximately more than 90% of the values will be here, or 95% of the values, at which point I am creating a breakpoint. So this is a general methodology of creating a breakpoint variable in R. Run it. Okay, I think there is some third one, two, three. Log price star. This has to be. Oh, I have to make it. There's a break. So a breakpoint is created. So 1745 rows we get, and at 1745 it will break, means it will not consider. So in our training set, we create a model based on our training set. So let us now initialize, now create our model for our ARIMA. So what we will be basically doing is, we will run the ARIMA model separately for the training set and for the test set, and use this. Once it is trained for the model is trained in the training set, we will apply the model in the test set and check the accuracy, right? So let's create a loop. Now I am using something called as a loop. So all these statements, if you would see, like for, if, while, um, continue, break, these are the type of conditional statements that we use in programming language. Common across most of the programming languages, even in R, it is the same. So you, um, I'm just explaining for people who are not into programming completely, right? So what I'm trying to do is, using the data in our, I'm trying to take all the data in our test set. What I will do is, let's see, for being from the breakpoint, that is 1745th row, all the way to end of the rows in our dlog price, right? We have to give a -1 because that's it starts from 0. I hope I have all the in. This is not right. I have to have one more. Yes. So if you will see what I'm trying to do, I'm trying to take all the rows from the breakpoint. So if I have say 1800 rows and 1745 rows are in my training set, I want them in the training set, and the remaining rows are in test set. So I am taking all the values in our test set. So what I have to do, I have to start from 1745 all the way to 1800, which is this. So what I want to do, by going from all the way from uh, taking all the values in our test set, we have to first create our ARIMA model for our uh, training set. First create our training set data, the which we will call it as stock underscore train. Let's use a dlog price, and from which row? 1 to B, 1 to breakpoint basically. This is our training set, and let's create our test set. What that will be? Will be from B to the end. So D log price, what value? B plus 1, all the way B plus 1, from all the way B plus 1 till the end of the rows, which is n row, basically D log price. I have to give a comma here. This syntax is a little tough here, but yeah, means as you would practice, it would become simpler. Training set all the way from 1 to B, test set all the way from B to the end. Not B plus 1 till end, right? So that is how we want to create. And the next thing that we want to create, we want to fit our training set data into our ARIMA model to create. So let's create a fit parameter. Acha, by the way, this assignment operator and this equality operator are almost this behave the same. This is not an equal operator, means I'm not comparing this is equal to this. Actually, I'm assigning this value to this variable. Why I am doing that? Because I want to fit my ARIMA method, which is called as arima.fit, arima.forecast. Basically, we want to create. So we will use a method called out as arima. You will see arima is a method that is available in, again, in time series. And we want to fit our which data, our training set data. So we fit our training set data. Here we will give our order. Now, order, if you will remember, we had decided it was going to be 202. You remember from our ACF and PACF test, we deduced the order of our ARIMA, which came to be 202. And we will say include, this is another parameter that we use. Basically, this is uh, a optional parameter that we are using here, which is we don't want to include the mean. So let's summarize our fit method, right? And now what you will see, the next is we have to forecasting. The next is about forecasting the log returns. So how we can forecast? So let's create a variable called as arima.forecast. And what we will pass here, we will pass a method called as forecast, which is again another time series method. We'll pass this forecast method into our data. Now let's see how we can forecast. Forecast, the value that we want to pass is fit, and we want to pass one variable called as h equals to 1. So one level. Only take the first level. If you know a autoregressive model, that is the first level that we are taking. Now let's summarize again. Summary arima dot forecast, and then what we will do is we can do a simple box test, box dot test. This basically tests the residuals. Nothing. Uh, this is not an important parameter, but in general, we use this method in our training set. Um, so let's create our forecasted return. So we'll create a variable. Now, if you remember, we had initialized a variable value called as forecast returns. Here we will be forecasting all the values for our that we will be passing, right? So in forecast return, what we want to pass is, let's see, row bind. What we will do initially, there are no rows. I want to bind one by one. So if you will see why we did this function for being breakpoint, I want to update this forecast return with this. When I created this ARIMA method, so this ARIMA method will run for our training set data and it will create values for our training set data. And in the forecast return value, I want to whatever the, so this method will for, then I created this forecast method, right? Where arima.forecast, I created the forecast method using this from the arima method that we had. So arima method gives us what is going to be the values based on the forecasted values at each period of time, and the forecast method allows me to capture those values and store it in the blank variable that we had. So forecast return, initially it is 0, each time it will get incremented, and I want to do it as arima dot forecast $mean. So a $mean, basically the mean values we want to use. So so that creates our forecast values. Now let's call the column names of forecast return. Let's give a column name to it. C, we call it as forecasted. What is forecasted is, that is the value that we are giving. Now, the actual, we also want the actual returns. What are the actual returns? Because we know the prices, right? The actual returns, we want to compare it. The training set value actually has, we want to compare what is the actual return and what was a forecasted return to know the accuracy of our model. That is how, based on our test set that we apply. So b plus 1 comma all the rows in from the log price actual return. I want to store the actual log prices of all the rows from the breakpoint onwards to the end, right? That is what I want to store. That will give me my real return. So real return, see, basically it is going to give me my real return, and I want to convert my time series object XTS actual return. So this creates our actual return parameter. So the final that we will call is mean actual, remove actual returns. I don't want to keep the actual returns. I want to keep the real returns. The real returns in the sense which are in time series format. Basically, we want it in the time series format. So hopefully everything is created. So let's run our, if there is no error. So there is some error. Where are the errors? I don't want to see the entire error. Let me use a code that I already wrote. So let me run this. Forecast return. I think this is, we didn't have the forecast return. Forecast return. This is the initializing. So let's run it. Now you see the ARIMA model is running. So for each value, it is creating a different ARIMA parameter. And we will see the accuracy percentage of our ARIMA methodology once it finishes. There were many. So you can see there are coefficients. You have the autoregressive. What are the coefficients for your autoregressive method and your moving average method? So basically, you have your ARIMA method and you have your standard errors also along with that. Now let us test the accuracy of our how much, what is the percentage accuracy that we have achieved using our ARIMA model. So let us do that using something called as comparison method. Now for that, let me use real return, and I want to store the last component, the last row for my, from the real return in this value. Um, and I want to use the forecast return, and I want to convert it into a time series object, extended time series. So let me do that. Uh, Forecast return, and then XTS actual return. XTS forecast return, and no, I will have to use the index method of real returns. This method's real return. So basically what I'm trying to do is I'm trying to create a time series object out of my forecasted returns and my real returns. So real returns are what has actually happened. So these are our actual returns. Real returns means what is the actual returns that we had, and we had our forecasted returns. So let me create a comparison value. So comparison, in comparison, I want to just merge to the real return with the forecast returns. Real return, and I want to the forecast return. That is the what I want to um, add, and I want to add a accuracy parameter to that, which I want to sign. I want to use whether it is negative or positive. If it is If my real return is, so in comparison, I have my real return and forecasted return. So if you will see comparison dollar real return, if this value, if my sign of my real return is equal to my forecasted, is equal. Now this equal to sign means is an equality operator. Forecast return means how many times we have predicted a positive return and it has actually happened positive, and how many times it has actually happened the opposite, right? Now let's print our comparison. Now let's what did you say? State real return, forecast return, list cannot type double. Oh, we didn't run it. That's why we had created this object, right? And now it will run. Now there is some error in the this. It's equal to sign comparison. I missed the C. So let me create comparison. Dollar forecasted sign comparison dollar return sign comparison. I think there is only one value here. So let me run this comparison. Created the comparison rate. This comparison is not the same spelling. Spelling is not. Let me. Yeah, now let's print over. So you see, you give the accuracy, means this has been my real return and this was forecasted return. So if it is the real returns are positive and my forecasted returns are also positive, then I give a value of 1, else I give a value of 0. So that is what we have done. Now let us see how many times, what is the accuracy percentage of us. So accuracy underscore percentage is what I will be using, and the accuracy percentage will be basically the sum of my where my accuracy has been equal to 1, right? So sum of comparison dollar accuracy, if you will see dollar accuracy is equals to 1. Now since I'm calculating a percentage, let's divide it by the total length, the total number of comparison values, right? Comparison dollar accuracy dot follow dot for forecasted, right? This is what we want to have, the accuracy percentage. Now print accuracy percentage. Accuracy percentage. Aha, the spelling is wrong. Now let's see our accuracy percentage. So we get an accuracy percentage of 52.45%. What does this actually mean? This is not a great accuracy. So what we are trying to say is more than 50% of the times we are actually predicting, this model is actually predicting the actual stock price movement that has happened in the 5 years, all the, in the or 6 years, all the way from 2015 till 2021 till date. 50, more than 52% of the time, our value have predicted correctly what has been the forecasted return. So you can use this model as is without change in the code for getting a forecasted. Now, this is just a way we use ARIMA methodology in forecast returns. So all these methods that we have discussed so far has been analyzing single stocks. If you will see, you can, instead of Amazon, you can pass any stock that you may want in order to use this method to see the performance in the future. Now, let's say now we have a, now we will get on to the next phase of our learning, which is called as, now we will create our portfolio. So once we have this devised our created our method for getting the right stocks in our portfolio, next thing that we want, what is the next possible thing that we will expect once we know that, okay, these are the high performing stocks in my portfolio based on this ARIMA trend indicators and all of that. What is the next logical way? Let's say I have 1 lakh rupees and I know that these 5 stocks have will perform very well in the next 1 year. I will, but still, uh, those 5 stocks may have, I need to know the weight that I need to assign to each one of the stocks, right? So suppose I have 1 lakh rupees, whether I should assign 30,000 to one stock and 20,000 to another, or how should I divide my portfolio? So that is where now I am going from single to multiple. So let us now move on to the concept of a portfolio. And let's see how we handle portfolio in R, right? So in R, we will let's, the first thing that as usual we do, we will import our libraries. So the library that we will be using will be almost the same, because the same libraries are used most of the places, which is quant mode, which is pretty common library. Now I will be introducing you the some of the other important libraries called as performance analytics. We have seen that, but I will introduce in more detail. Portfolio analytics, very important library. Then another library I want to introduce is something called as ROI, return on investment. Very important factor. Another library that we want to use is within ROI. I want to use something called as ROI dot plugin.glpk. This is another library, and another library that I want is something called as ROI dot quadprog. All these libraries I need. Now let's see if they are installed in my environment. It's there. So everything got invoked in our environment. Now I have identified 7 stocks which I think is going to maximize my investment in the next 1 year. And I want to store them. So the 7 stocks, let's store it in one variable, which we will call as tickers, right? let's call them. So Facebook is one, Amazon is another. Let's say Netflix is another, and Google is another. Then I have SQ, Sequoia, and NVIDIA. So these are the stocks that I have selected based on my various technical indicators and all of that that I have identified. They will perform well in the next 1 year. Let's say for everyone it might be different, but for me, like these are the seven, right? So let's see how we can create our portfolio, right? So the first thing that we do is we create a portfolio prices. Initialize it to null. Let's initialize it to null. So I want to store the portfolio prices of each of these stocks that we have seen, or the securities that we have seen, in column format. The all the closing prices of all these seven securities I want in column format, side by side. How we can do that? Simply calling the for loop in R. So for loop gives me the effect. For ticker in tickers, what I want to do for ticker in tickers means for each ticker, for each one of these securities, what I want to get the portfolio prices. So portfolio prices. So portfolio prices, now portfolio prices are what I want for each one of these securities. I want the fourth column from each of these securities, right? So, and I want to bind them side by side. So I will use a function called as column bind, right? So portfolio prices, initially it is null, it will gradually one by one, it will get added. So get symbols, get symbols dot Yahoo, our very old friend, get symbols dot Yahoo. Now here what we will be passing is something called a sticker. So what this is doing is it is taking each price, each Facebook, each security as one ticker, and it is auto incrementing. So for the first ticker, for first Facebook, initially portfolio prices is null. So it will be, this is null initially. So null, and then get symbols of this ticker is for the first time it is Facebook. So Facebook, let's say I want the data from 2016. From 2016, let's say I want from 0103. Let's say I want the data from this periodicity from this. And periodicity I want is daily basically. This is not necessary for me to give, but yes, this is one of the parameters that you should know. We give periodicity is basically daily, and auto assign we already have to auto dot assign. We know we have to give F. And what I want basically is the fourth column of each one of the tickers, right? So I get the fourth column of each. So initially this is null. Here it will Facebook closing price of Facebook will come and sit on portfolio prices here because we are assigning it to portfolio prices. Now portfolio prices has closing price of Facebook. Next it will get Amazon, and it will column bind it to Facebook's Amazon price, and then store it. So let's run and see how it looks like. That is where you will be more comfortable. Always. So we got our portfolio prices, and you see the closing price of 1, 2, 3, 4, 5, 6, whatever stocks we have selected. The closing price of all the stocks, which is a fourth column in each one of them, has been populated in this table. So we have successfully created a selected our portfolios, the closing prices of our portfolio. So that is the first step we have in portfolio creation, which is selecting the right security. The most important thing in a portfolio is selecting the right security. Once you have selected the right securities, you have to know in what proportion you're assigning and what is going to be a trading strategy also again. So with that also we will discuss. So let's say in this case, I will use the ROC method for getting the portfolio returns. So let's use our ROC method. We can use the differential log return also, but right now ROC will also give us a good result in terms of getting the returns. ROC is also similar to the differential log returns actually. It's also basically a differential log return. Portfolio prices. So let's run it. So your portfolio returns got created. So these are all your returns from your portfolio returns has been created. Now comes the most important part. We have to define something called as constraint, and there is something called as objective in our strategy. What do we mean by constraint and what do we mean by objective in our strategy? By constraint and objective, we mean that we are objectifying our portfolio creation. Which in turn means that we are creating a rule saying that say for example, the rule I want to create is I don't want any one of these stocks to not to get a share in my investment amount. Let's say I want to invest 1 lakh. I want at least some amount of money to be invested in each one of these stocks. So let's say I want to say that the minimum weight that each one of these securities can have, let's say it is 10%. So 10% will be assigned to these stocks, minimum 10%. And I also want to say that none of these stocks can have a weight of more than 40%. Similarly, I want to say that I don't want to have any short position. Short position means I don't want to create a situation in which one of the portfolio gets a negative weight. It is possible that the weight can be negative for a portfolio, means that our model is asking us to sell the stock and encash it to buy other portfolio or buy the other securities. I don't want that also to happen. That also rule I can create. So all these different rules I will be able to create when I create my portfolio object. So the portfolio object, in order to create our portfolio object, we use which we call portfolio specification. We use a method called as portfolio specification. So the method that is used is called as portfolio dot spec. This is the method that we use to create a portfolio object that will have the constraints and that will have the objective. What is the parameter that we pass is the column names from our portfolio returns. So from our portfolio returns, the column names that we are getting, we are passing it to our portfolio specification or our portfolio object. Now comes the most important objective, which is to assign the constraint and the objective to our portfolio specification. Let's see how we can do that. Add dot constraint. The method that we use is called an add dot constraint. If you see, add dot constraint is a method on what? On our portfolio object. And what is the rule that I want to create? The first rule that I want to create is I want 100% of my amount to be allocated in all the stocks. So the rule that is available to us is called as weight underscore sum. Weight underscore sum tells me that all these portfolios will have a minimum 100%, means all my 1 lakh amount will go in the investment. So I have to give my min sum equals to 1 and max sum equals to 1. Right? So it means that I don't want to have any sell short position and all. I want to invest my entire 100% portfolio in these 7 different securities that I have. The next thing that we want to do is I want to create another constant. Like I want to say that again, the minimum weight that can be assigned to any one of these securities is something called is minimum 10% and maximum 40%. Let's see how we can add that. So for that, the method that is available to us is called as box. The method that is available is called as box. And here I can specify my min equals to 0.10 and my max equals to 0.40. I can specify my portfolio's constraint. We will look at few more constraints once we complete our model today. Then we can have a look at some of the other constraints that we have. But or maybe tomorrow we can see if we are left with no time today. That is fine. But these are some of the key constraints that we add. The next constraint that we add, the next method that we add is called as add objective method. If you will see, there is something called as add objective. So objective is to basically remains very simple. Maximize my return and minimize my risk. That always is the most common objective. Now there are certain variation even in objectives. People may want to see, if you want to minimize your risk, by default your returns will also be be lesser only. But some people might have an objective that they can take more risk in order to get higher returns. But the type of portfolio that I want is give me the most optimum portfolio, means where my returns are most balanced, corresponding to a given level of risk, which is basically told means given to us by the efficient frontier, right? Ah, just a second, guys. So that is what is given to us by our efficient frontier. So let's look at how we create our efficient frontier. Here we have to give the mean. So what I want to maximize my return, and my returns are basically given to me by my mean, right? So that is what is given to me by my mean. Next objective that I have is something called as minimize my risk. So type equals to risk, and risk in a portfolio is generally defined by standard deviation, as we all know. Risk is always defined by something called as STD, right? Standard deviation. So let's add these. So let's first create our portfolio specification. It got created, and add the objective and the constraints. Uh, there is some error actually. Yes. The constraints got added, but the objective of a standard deviation also got added. The mean is type equals to return, name equals to mean. Oh, comparison with this. Hmm, there's some spelling mistake here, I think. Let me see. Hmm. So let me run this. Yeah. Um, Previously we didn't have this dash here. That's why. Anyways, so now if you will see, your port F has your constraints and objectives being added to it. So there are two constraints and there are two objectives that are added to our portfolio object. The next thing that we want to do is create our optimum portfolio, right? So what is our so optimum portfolio is, let's define our optimum portfolio by the method called as optimize dot portfolio, and here I want to pass my portfolio returns Along with the portfolio returns, I want to pass my portfolio object that contains the definitions of my constraints and my objectives. And I want to use an optimized method based on my return on investment. ROI is the method that I want to be the my method of optimization. And let's say I say trace equals to true. So let's call this, run this method. So my optimum portfolio is created. So I see that, you see, the weights got defined for your optimized portfolio, right? The weights, now let's chart our weights. Chart weights. Now chart weights of my optimum portfolio. So I want to see what are the weights that got assigned to my optimized portfolio. So let's zoom it, and you see that what 10% was the so now let's look at our objectives, our constraint and our objectives. What was the first constraint we had added? We had said that maximum 100% should be allocated, all entire 100% should be allocated to all my six securities. So 10% plus 10% plus 10% is 30%, plus Google 40%, plus 25% is my is basically my SQ. So 25%, 40, 65, and 35% is my NVIDIA. So it's 100%. The entire 100% got allocated in my, for all the securities. Minimum should have been 10%. So none of the securities got a value of less than 10%. And the maximum was 40%. So none of the securities got a weight of more than 40%. So maximum was 35%, which was allocated to NVIDIA. Now, based on that, it will create my most optimized portfolio. Means given a given at a given level of risk, what is the best return I can get? So that is what my optimized portfolio and these weights are telling me. So if I had to use my own method of weights, I would have perhaps said, okay, I have 6 stocks, I have uh, um, I have so let's allocate 15% to each or 16% to each in order to reach 100%. But our optimized portfolio is saying that no, that is not the right way. Your allocation of the weights for each of the stocks should be different, or for each of your securities should be different for you to get a best return, right? So that is what this method is giving you. Now let us look at, so let us create our efficient frontier. Efficient frontier, as we all know, is at a given level of risk, what is the best. So let's extract our efficient frontier. So extract efficient frontier is the method. What, from where I want to extract my efficient frontier? From my optimum portfolio, optimized portfolio. Now here we used some, we used some parameters which is not necessary, but like standard deviation was our risk factor, so that we can match one of the columns. Now let's say I want to limit, so to 25. What I mean by that is, let's say given these constraints and this risk, how many permutation and combination can be possible? Maybe thousands, hundreds also, right? But that will take a long time to execute. I want to say that, okay, the first 25 that you find best, out of that, give me the best. result. So in order to save time, right? So in big programs and all, we don't give this number, and um, that is what I want to do. Risk aversion is another uh, parameter that we use. And let's say I am not averse to risk, means give me the best returns given a at a given level of risk. At a given level of risk, give me the risk return. So I am not the type like who is more interested in a PPF kind of a or a post office kind of a return of a fixed kind of a return. I'm more interested in knowing which of the which at what is the most efficient combination of the stocks which can give me the best result. Sorry. So let's uh, chart it out. There is also called it. We will have to let's keep a little bit of patience to have the charting done. So let's chart it out. Our so there will be a lot of um, parameters that we will use in this. So just a little bit of patience will help you. So these are all the parameters that you should be passing here also. Then there is something called as xlim. I don't want to have x limited any to null from sorry equals to null. Now let's define something on the size of the or the line size of our graph. So these are all uh, optional parameters. You may not need it, but good to know all these uh, elements are there in a, while creating the optimum portfolio, right? Let's use dark gray color also of the line that you will draw, that also you can. Then what will be the main text? So what we are creating is efficient frontier is what we are creating. So that is the main text that we want in our graph. So that also you can print. What is a text type? So you can use something called as rar, not so the text type also you can give. Let's say SR I want to use. Uh, RF equals to 0, risk-free rate 0. I am taking as a. I want the tangent line, right? You know the tangent line um, in a efficient frontier that I want to get, which is I want my mom mark it as true. Um, let's give the legends also as true. So legends also I want legend size basically is 0.8. CX is basically the legend size. Then something also we use is all called as chart dot assets. Chart dot assets is something that we use. Chart dot assets I want to mark it as true, and there is something called as labels dot assets that also we will mark it as true. The next thing that I want to add, uh, the pixel size basically of the assets. Let's mark it, keep it to 21, and cx dot assets is to 0.8. So let's create our efficient frontier first, run it. So our efficient frontier got created. I will remove this. Now let's see how it runs. pch.assets.not found. Hmm. Or if we could tangent is this 21. All right. So you see, you got your efficient frontier finally, based on the portfolio that you have specified, based on the portfolio that you selected. You got your efficient frontier. Now, if you see the tangent line where it crosses this graph, that is your most optimized portfolio weight combination that you should be using for your, as per the given efficient frontier, right? That is going to maximize your now. If you see why this tangent line is touching here, why is it not touching at why this tangent line is touching at the position that it is touching the frontier? Why is it not at some point below the in the graph? If you see, the graph is like a curve, right? It touches it at a certain point. Why it is not more? It does not have a higher degree, or it does not, it does not have a lesser degree. On what it determines? Can any so basically, if you will see, after this point where the tangent line crosses this graph, your returns almost stabilize even with additional level of risks that you are taking. Hence, even if you take additional risk, your returns are not going to be affected much. So why take additional risk? Till this point, yes, additional risk was giving you a good enough level of returns, which is not the case after this. Hence, this tangent line is gets drawn on this efficient frontier, and this gives you the most efficient combination of your weights, or the portfolio, the most optimized portfolio for you to be used in your uh, general scenarios. This is about the efficient frontier. This is how we create an efficient frontier in uh, in R. I'm pretty sure that there are lot of variations you would have used in many of the other in other tools. Like many people use Excel. Or we can create very good, nice graphs in Excel. Also, we can create it in other. There are many other tools where we can create these kind of graphs. But R gives, and we can. I've not added even. If I used something called as ggplot and all, we could have decorated this efficient frontier much more, but uh, we have not used. That's a different altogether R package for beautifying your graphs and all of that, right? Adding more color, adding more uh, vibrance to your graphs. So that is how you create your efficient frontier and all of that. Now, having said that, so that is what is our efficient frontier looks like. Uh, with this, I think we have covered quite a bit. I will like to know if you have any questions before we uh, start a next topic, or probably if you want to discuss any of the things, because we covered a lot of things today with respect to ARIMA uh, and the various methods that are being used in ARIMA, decomposing a time series, uh, then performing the ACF, PSEF test, uh, to the ADF test, to getting the comparison in the values. Then we went on to get the most optimized portfolio for the selected securities based on the returns, and then creating our uh, constraint and methods and objectives for our most optimized portfolio. Based on that, creating the efficient frontier and getting the most uh, best combination of weights that can give us the best results for us for our investment. And how we create that in RV, we saw entire things. Now let me pause a bit and get some questions if you have any.
Participants, you are having any queries, any questions to ask from
Even from
sir?
the last class, if we have.
Yes, yes. Also from the last class, if anyone wants to ask anything.
No questions?
I guess, sir. Yes, I guess, sir. We can move ahead.
Okay, perfect. So far, like we have covered most of the things that I had to cover today. The next important thing that I wanted to discuss was on the different type of constraints that we are having, right? So as I mentioned, the two types of constraints that I discussed with you, where the first constraint was with respect to the box constraint, was the minimum weight that we need to assign to our portfolio. Now, there are few other constraints also uh, that we use uh, in our portfolio, in portfolio management, right? Sometimes we need to take a short position. Let's say we have to take a short position, in the sense I also want my constraint to include a short position. At that time, what I will say is, I will say that I will use a method called as, let's say, position limit constraint. Position limit, let's say I will use, we have a maximum number of 3 assets, and I want to say that we add a position limit allows the user to specify the limits on the number of assets with respect to the number of short position or long position that we want to use. The way we add it is, let's let's add it here itself in our portfolio. And let's add dot constraint, and we can use a method called as type equals to position underscore limit. And in position underscore limit, I let's say max position I want to say is 6. So this is how I can number of, so this is the number of long and short positions, non-zero positions that I need to take. This is what I also can add here. If I let me run it and see. Um, this is a bracket is position is around. So that position got added. Now let's chart our weights and let's see if it changes any. It didn't change our weight positions because I gave all the 6, right? Max position, let's say if I give 4, what happens? But I have given this constraint, which is 100% allocation. So this will not create a short position mostly. It got added. So chart weights, it again didn't get changed because I am given this as let me um, mm, um, put um, remove this and then add only the what do you call as, let me call this, and let me add these, and then let's see if my position changes. Okay, still not it join changes. So still it says that uh, my maximum position is, let's even hide this and create this, and let's optimize our portfolio. So it still creates the same almost, if you say it's, but it is slightly changed in the sense, if you see um, now the weights are your optimum portfolio weights have slightly changed to 54346, little bit, not much. So it's still almost the same that what my um, other positions are saying, right? Similarly, I can have some other type of uh, constraints like um, I can have a return constraint also. Uh, let's say I want to add a constraint called as turnover. Let me another constraint which is called as turnover. What does this turnover concept mean? A target turnover can be specified as a constraint. So the turnover is calculated from a set of initial weights. Um, so let's say I want to have a return target of turnover target of 0.2. Turnover underscore target. Let me say 0.2. This also I can have. Let me see, it gets added. So this gets added. Now if I put it, it remains almost the same given the other constraints and all. But what I want to say is, similarly, we can go on as we have more knowledge about the different type of constraints. Um, we can go on adding constraints. and we can define how we want to create our portfolio, and we want to define how we want to create our objectives also. And so there is an entire CRAN package which tells us on that. You can go through that, which is available in CRAN. If you have to study the different type of um, uh, these uh, constraints, I'm giving a link to you one of the CRAN projects in R, and you can have a look at them and see if that that makes sense to you. So with that, I have covered almost all of the topics that I needed to cover for today. We'll continue with our session from uh, in the next sessions. We will be discussing about the kappa model, the alpha beta, the Sharpe ratio, and a few other parameters in portfolio backtesting in portfolio management, and a few other concepts that we want to see. So having said that, I will uh, I will I would like to close the session for today, and thank you all for your time for and patience to look at this complex coding and all of that. Right.
Thank you so much, sir. Rather, we should say that it's been, quite we are privileged to have you, as a research person. And, this is, we are doing, in the third phase also. So thank you so much, sir, for like sparing your time. And participants, tomorrow we are going to continue with Pranvesh sir's session at 2:30 p.m. sharp. Thank you so much, sir.
Thank you. Thank you all.
Been always wonderful to have you here. Thank you so much.
Thank you. Thank you all.
So participants, feedback link is already being shared in your WhatsApp group. So kindly fill the feedback form. And for tomorrow morning, we are going to have an excellent session from Dr. C.P. Gupta at 10 a.m. And Dr. C.P. Gupta is going to take session on data visualization and representation from Excel, right? So through Excel. So it is going to be first two sessions Dr. C.P. Gupta is going to take on data visualization and data presentation. And post lunch, we all will be back with Pranvesh sir, where we are going to see the CAPM model and Sharpe ratio and back testing. That is what Pranvesh sir has said just now. So yes, so I'll just sign off. And thank once again, Pranvesh sir, thank you so much. And we all be together tomorrow at 2:30 p.m. Thank you so much, sir.